first, because every time you change the source file, you have to reassemble first to update the object file, and then once you update the object file, you can relink it. All right, so this time everything works. So I can use GDB to debug the program, list the program, so I can stop on the first instruction. Remember, I cannot stop on the very first instruction, so I'll stop on line 11 instead of line 10. Run the program, and now the program has stopped, but everything is now loaded. Okay, it has loaded all the memory content that we were talking about a little bit earlier. Let's go ahead and find out what is at label L1. Okay. Now to do that, you have to use the X command. The X command is going to be very, very helpful in this class. What is the X command? Just type help. Just like my notes, GDB help tends to be extremely terse. All the information is there, but it's very concise. Okay, it's very condensed. So we'll just take a quick look here and see what X means. X means examine. And FMT is the format. Okay, how do you want to format the content at a particular address? And address is really just a memory location. And we have several formatting options. We can print something as in octal, hexadecimal, decimal, unsigned decimal. Now that means this one is actually signed decimal, and this one is unsigned decimal. Sorry?
Oh, is it negative 1.7?
Is that negative?
Oh, is it negative to positive with sign? This one starts at 0.
Well, signed means it is interpreting the bit sequence as a signed number. Now we'll talk about what is signed, what is interpreted signed, and what is not interpreted signed. So we'll talk about that later. Because for now we're not going to deal with this. You can print something in binary, which comes in very handy occasionally. Float and float we are not going to use. You can use I to disassemble. You can print something in character to decode the byte, so you can actually see the equivalent character. And you can print something as a string, and basically you can just print out multiple characters at the same time. It's handy. And then for each item, you can also make it a byte. You can make it a half word, which is extremely confusing here again, because a half word turns out to be the same as a word in dot word. Okay, a dot word is 16-bit. A half word in the debugger is 16-bit. Because a word is 32-bit in the debugger. Okay, so you just have to remember that. Okay, in the debugger, a word W is 32-bit, but in an assembly language program, .int is 32-bit. In the assembler, half word is 16-bit. In the assembly language program, word is 16-bit. Okay, so little things that you have to remember. All right, so let's go ahead and do something about L1. Okay, we want to look at what is at L1. Okay, so we'll say x slash. Now, since those two items are defined as 16-bit things, and there are two of them, so 2 is the count. How many of those things do we want to use? X is half word, and then x is hexadecimal, and then we'll say L1. Okay, I can tell you right away, this is not going to work. Because when we use L1 like this, it is actually doing it's going to do a dereference using L1. So for now, we'll just say that, oh, I guess it does work. Because before, I had to change it to ampersand, so they have changed the assembler to be slightly more intelligent. Okay, so I stand corrected, it does work now. For those of you who don't believe me, you can actually check back my notes from last semester and see whether that worked last semester. All right, so this is okay. We are at label L1, and we are seeing the first 16-bit is ABCD, and then the other 16-bit to be exactly 5. Is that what we're expecting? Yeah, I think so. I mean, I can open up another terminal to look at the source code. Okay, so let me start another terminal, go to the same folder. Oh, wrong year. so going back to the source code, we can see at label L1, we have 116-bit quantity specified in hexadecimal as ABCD, and then the other one is just 5, and that's exactly what we are expecting. Okay, that's very good. What about the first dot int? How do we get there? If L1 as a label is the address of ABCD, the dot word ABCD, what do you think would be the address of the first byte of the dot int?
L1 minus, we're looking 2 bytes.
Well, dot int is 32-bit,
4 bytes.
so we're talking about 4 bytes, 4 locations. So we'll give that a try. This is I think this will not work for sure. Okay, so we'll say, but this time we have to change the way it is printed because we have one single thing. The 1 is implied if you don't specify a count, it is defaulting to 1. It is W because remember in the debugger a word is 32-bit, and we want to keep it in hexadecimal because the original definition is in hexadecimal. And then we print it and it worked. Okay, so they definitely have changed the debugger to make this work. Before you have to go through a lot of gibberish to make this work, but now it's easy. Okay, so you guys are lucky because they have updated the debugger to be a little bit more user-friendly. Yes, this is user-friendly. Yep.
So what was the first number represent? After the X slash?
After the X
One word.
slash one item, and that item is the W, which means it's a 32-bit, and the X means I want to print it in hexadecimal.
And the other one is
The other one is printing 2 items, each one is a half word, which means each one is a 16-bit quantity. And I also want to print it
So it's 4 bytes after the address for L1.
All right. So are there any surprises at this point? Nah, no surprises. But after all, I have one question. If you look at this location, L1 minus 4, now we calculated the location correctly because it's a 32-bit thing and it's right before L1. Okay, so we did the calculation correctly. But if you look at this 32-bit thing, which consists of 4 bytes, the question is, how are those 4 bytes arranged? Okay, there are 4 bytes. Okay, we know the content of those 4 bytes. 1 byte has to be FE, 1 byte has to be ED, 1 byte has to be ED, and 1 byte has to be AD. The question is, which one has the first memory location and which one has the last memory location? That is the question.
Is it the opposite?
Hmm?
The most significant number is to the right,
Well,
the least significant is to the left.
We'll take a look. Okay, so this time we're gonna go to location L1 minus 4 again, but this time I'll print out 4 different things. Each one is only a byte, and I still want to print in hexadecimal, and it becomes kind of odd because FE was the most significant byte of the 32-bit, and now it is the rightmost one. Okay, the one on the right, and then we have AD being the least significant byte in the 32-bit quantity, and now it is listed all the way to the left-hand side. Okay. It's printed like this because the Intel i386 architecture is known as a little endian processor. Little endian means the least significant byte has the lowest address. Are we doing okay so far? Because with a 32-bit thing, you need multiple bytes to store it. Now, if we require multiple bytes to store an item, then there's always the question of which bytes is stored first. Are we storing the most significant byte first, or are we storing the least significant byte first? The choice is somewhat arbitrary. There's really no distinct advantage to one or the other approach. The Motorola processor 68000 and all its derivatives are big endian. In other words, we store the most significant byte first. Intel architecture, the entire family of x86 processors, they are little endian processors where we store the least significant byte first. TCP/IP as a networking protocol is also big endian, which means it transmits the most significant byte first. Okay? Now these things are important because when you're dealing with TCP/IP, you have to make sure an Apple computer, from way back when using the 68,000 computer processor can talk to an i386 processor. So the ordering of the bytes has to be kind of fixed, okay? Has to be switched around if the architecture natively is not using a big endian notation, big endian convention like the x86 architecture.
What does that mean, endian?
Endian, E-N-D-I-A-N, basically it specifies to you which one is at the end of the sequence of bytes. So little endian means the least significant byte goes first, or has the least address. But that explains why when we print it out as individual bytes, AD is the one that comes out first, because when we print items like this, the first item, or the item that has the least address, is printed first. And AD is the least significant byte, has the lowest address. That's little endian. Are we doing okay so far with this concept? Okay, all right, very good. What about this ABCD here? Okay, let me go to label L1, and we'll print it as 4 bytes also. What should I be seeing in this case? If I press the Enter key, what should I see on the screen?
0.
It's a trick question, right? Okay, so we know that ABCD has to be the lowest 2 bytes, okay? Now, between those two, we can switch them around, but we know that the first 2 bytes has to be ABCD in whatever order, and then the next 2 bytes has to be 0, 0, and 0, 5, and once again, we have to kind of figure out the order. Within the first 2 bytes, ABCD, CD is the least significant byte, so it has the lowest address. So when I print like this, using this particular command, the first byte is CD, the next one is AB. That will deal with the first 16-bit. The other 16-bit is 0005, and once again, we will print the least significant byte first, which is 05, and then we'll print 00. So the entire thing will come out as CD AB 0500. Okay, is that okay or not? In terms of concept, most people cannot switch the bytes around quickly enough, but I'm asking, do you understand the concept of what is little endian? Okay, so let's go ahead and press the Enter key. I have known to be wrong, but the debugger will fix. Yep, that's exactly the way it is predicted. All right. Any questions at this point? No questions? All right, how about this one? I always can throw some really strange curveballs here. What if I print one 32-bit thing in hexadecimal, and this time we specify the first location to be L1 minus, I don't know, let's do L1 minus 3. Okay, now this is not really a curveball per se, because once you understand how the individual bytes are arranged, you can then reinterpret those bytes and say, oh, okay, so we are stringing these 4 bytes together to become a 32-bit integer, and so let's go ahead and figure this one out. Okay, and to do this, I'm going to use a mouse pad and make it a little bit smaller because it's taking up the entire screen. All right.